All right, Johnny, are you excited? Future of Data episode 2. And it looks like a lovely evening over there in Romania. Still bright outside. What time is it?
9 p.m.
Oh, magnificent. Well, today we have some fun stuff. I put together a nice little slide deck so we can have a bunch of visuals to be going through and adding to. And my goal is to make this public with everybody who is on this chat. And I'll make sure that we have all these links tweeted out. Next week, I will go and take our fancy image for the future of data and replace our title slide with it, which will be a lot of fun. But for today, what we chatted about last time was that we were going to dive a little bit more into, the cryptographic guarantees of immutability and, how sort of we look at the future of data security when it comes to Web3. So I thought, to start off, talk about like some of the current storage solutions that are out there, like IPFS and Arweave, or even storing in smart contracts directly. And for me on this one, I actually think it's more important to talk about like the dangers of this methodology and sort of how, let's say, Web3 has materialized to date for data storage. So, one of the things that we are pretty like cautious of at Weavechain that we ran into when we were starting our product was that we actually felt like most data could never exist on the public and permissionless version of Web3. So, whether that's storing data directly in a smart contract, which is, very expensive to do and challenging from a technological perspective, or storing it on services like, IPFS, Arweave, Filecoin, or accessing via Ceramic. The challenge with these methodologies is that they don't satisfy global compliance needs, GDPR and HIPAA. And, we think most data in the world needs to satisfy these global compliance needs for everything from healthcare to compliance data. And, the reason that, public Web3 data can't satisfy something like HIPAA compliance, for example, is because it has no physical safeguard associated with it. So most commonly, if you're going to go and put sensitive information in public Web3, you'll go and encrypt that data, which is what HIPAA refers to as a technical safeguard. Encrypted data is great. It makes sure that you can't go and, let's say, actually understand the data, even if you can access it, unless you have the keys. The problem is it's only one type of safeguard, and HIPAA compliance requires a physical safeguard as well. Meaning that you would have to actually firewall the data so that somebody can't access, even the encrypted data unless they were a permissioned party. And this is like a very common pattern for enterprise software. I would argue that it's like, one of the like classic protections that somebody has when they are trying to go and protect their internal assets is they just don't let anybody have a copy to begin with. Let me see if I can pull up a different slide for this one to talk about how we think of protecting internal data in general. I usually like to say that if you're going to go and protect data in even a Web 2 world, there are some very common things that you do. And really, the first step is that firewall. Let me see if I can pull up this slide really quickly. Here we go. I'll move this to our common deck in just a second. But if I were, trying to lock down a data set today, I would go and put it behind a firewall to make sure that nobody could access it. I would make sure that even if you were within the network, you could only access the data if you were properly permissioned. Then you encrypt the data at rest and you encrypt the data at transit. And ideally with Web3, you are adding immutability guarantees and distributed defense on top of that. But if instead we have to use a public Web3 solution that gets rid of the firewall entirely, I would argue that you've actually, gotten rid of your first and one of your most important lines of defense. Now, this is just for HIPAA compliance. The other tricky thing about public Web3 solutions is that, they don't have the ability to delete data, which is required for GDPR compliance. So this is commonly known as the right to be forgotten. In technical terms, it's referred to as an erasure obligation. And the trick is that you can't erase data from public Web3 because it is immutable as a feature, right? It's like one of the benefits of blockchain is that you can't actually go and delete data. So, if you put data on Arweave, the permaweb, again, one of the key things is like that you can't delete the data that one's over there. On services like IPFS, it's a little bit more nuanced. Whether data maintained on IPFS is whether it's still active and pinned and accessed by users, but there's no like delete operation that you could actually run to go and satisfy this erasure obligation that you have as a company, which makes it pretty challenging. And again, if you're putting data directly into a smart contract similar to Arweave, that data just can't be moved over here. So we were trying to figure out how we could go and establish these Web3 datasets with Weavechain while still satisfying these compliance rules. And the solution we came to was a technique that we've been calling blockchain anchoring. And the idea is that if you go and create a hash or a zero knowledge proof of data, what you're doing is saying that like this data will always be able to create this one-way hash, for example. And this one-way hash could never be used to recreate the data. So we could go and put this data onto a blockchain, the hash of the data on a blockchain without breaching GDPR compliance. And the blockchain is going to go and make sure that nobody is capable of, inserting new hashes or removing those hashes without being properly permissioned. And the last thing I'll mention over here is that if the data is changed in any way, shape, or form, it would never go and recreate the same hash with the same hashing function. So if we do have this, sorry, go ahead, Johnny.
There is one thing that we should add here, the fact that the hashes that we create are salted. Actually, we support a wide range of hashes. It's configurable. You can use SHA, you can use Ketchak, you can use even, I don't know, Blake2 or SHA with Sphinx, so you can use quantum-resistant hashes if you want. But the salt, which is known only to the private network or the people that are part of a data sharing agreement, make sure that somebody is not able to do a dictionary attack or to see that the same piece of data is hashed twice in a data set.
Oh, I like that one. How does that work with the salt though? So is it that like the salt actually changed over time? Or like how would you prevent the not seeing the same data used twice?
You just change the salt.
You change the salt and you know that.
This is again something that we configure on our side. By default, we use the same salt. So it's just obfuscation. The same piece of data will have the same hash, but we can have a deterministic generation of salt for the members of the data arrangement.
Oh, that's really interesting. A deterministic figuring out what salt you're going to use. That's an especially fun one. And if you're doing a time series database, the data is always changing anyways, right? So append only always grows in size, so you should never have the same data that's being put in there twice. Well, the cool thing about this again is that we can always make sure that the data hasn't been tampered with by showcasing or using the data to go and recreate these hashes, using that salt as well. The blockchain is going to go and make sure that we, let's say, have an ordered series of hashes that can't be tampered with, for insertions, deletions, you name it. And we actually really like using public blockchains for this because if you're using a private blockchain network, the danger is of collusion, right? So if we, just had a private blockchain network between A, B, and C, and A and B decided to cheat, well, there's no way that C can actually prove that they cheated. The blockchain, they can alter the blockchain record and claim that it's correct, and they would have a majority consensus over here. If you're putting this data on Polygon, for example, that's not possible. If somebody is able to go and crack Polygon's, consensus algorithm, they have much better things to be doing than, let's say, messing with your hash history. They're going to go and be withdrawing funds. Now, these methods are so powerful that, in 2021, the White House actually issued an executive order to go and say that they need all government logs to be utilizing these properties. So definitely, I assume that the U.S. federal government is utilizing mostly private blockchains for storing these hashes. But you see here, it's that logs should be protected by cryptographic methods to ensure integrity once collected and periodically verified against the hashes throughout their retention. That's exactly this methodology, and it guarantees that nobody's going to go and mess with these security logs. I can actually jump into that example really quickly because I think it's a fun way to sort of visualize what people are trying to protect against. Let me see where I have that particular slide, though. it's been so long since I've played with this one, Johnny. Do you remember our old security scenario for log protection? I just showed it to somebody
Yes.
this morning as well. Ah, I found it. Our old MITRE attack. So let's say that you were going and trying to protect your security logs locally in your network. Let's see here. So you have your firewall set up, your environment with some special resources and security logs. The issue is that if you are operating in a zero trust way, you assume that somebody is going to be able to breach your firewall. And the trick is that upon most intrusions, hackers will not only perform some malicious activity with your resources, they will then go and tamper with your security logs and cover their tracks. Now, if you were going to go and try to create immutable security logs using blockchain technology, what you would do is say that we are going to go and have those security logs replicated with a blockchain, so that even if somebody goes and infiltrates one environment, they actually can't go and tamper with these security logs and cover their tracks over here. This is like a really simple use case where you could see the ability to have immutable data helpful in an enterprise style environment. Now, one of the other cool things about the methodology of anchoring here is that let's say it makes the data really, really self-sovereign. The data itself is actually never leaving your network. And I find that to be very cool because for the reasons that we just described earlier, the whole GDPR right to be forgotten thing was actually made to support user rights. It was based off of what is best for individuals. I want the ability to go and have my data be forgotten from specific networks. And, whenever we're talking with our customers about potentially utilizing healthcare data with Web3, we really caution them against putting, consumer health data on any of these public Web3 services, because it's scary that that data would be out there in the open, available for anybody to download in an encrypted fashion. Because let's say that quantum computing comes through and suddenly 2023 encryption is not valid in 20 years, suddenly they're going to have access to, my entire electronic health record that has been posted on these services. And there was a really interesting article that was posted by, Vitalik just this past week that was talking about the transition of blockchain technology towards more privacy-centric use cases. And one of the ones that he mentioned was at a recent conference in Zuzalo, they had a new network that they were, a new product they were building with ZooPass that was using ZK snarks to manage identities. And they built a POAP product called these, Zuzalo stamps, which are kind of like POAPs over here. And the interesting thing about them is that they actually made it so that the data for your stamp was held locally on user devices. And all you were actually sharing with other people was a zero knowledge proof to show that you had a stamp, without actually sharing any other information with any other party at any time. Now, there are risks here, right? If you lose your local information, you lose your stamps. Same way that if you lose your keys, you lose your coins, kind of thing. But I like this. Self-sovereignty is a good thing for me in these scenarios. I think that it's actually the best thing that you can do with data. And I'll add on top of that, a lot of our customers are trying to go and figure out the, let's say, the theoretical migration between, let's say, today's SaaS world, where everything is stored on centralized servers, the public Web3 world where everything is stored on these public and permissionless solutions, and a self-sovereign world. And we hope that really you can go and have that be a choice of users for what they want, whether it's really high levels of convenience or high levels of privacy. So if I could explain that in a little bit more detail over here, one of our customers is Genobank, the company that lets you go and sequence your DNA and have a NFT that represents access rights to that data for use in a variety of purposes. And in the first version of a product that we built for them, it's mostly a SaaS solution. So you sequence your DNA, and they'll go and hold your data on a server that they control, and then they'll give you that NFT that represents access rights, so you can go and share that data with researchers or use it in a marketplace to understand more about yourself. But in the ideal scenario, we would enable dynamic data governance for the Genoverse, where you as a user could choose whether or not you want to have GenoBank hosting your genetic data, or if you want to host it yourself on your laptop and have that local custodianship risk, or even have a third-party data steward hosting your data. So a company like Skyflow, for example, whose entire mission as a company is just to go and host the gnarliest data sets in the world for users, whether that's financial data or personal health data or healthcare data. Now, once you have solved this governance challenge, then you can go and do things like providing access with NFTs, utilizing confidential computing to enable research without breaching privacy, having a lineage so that people know how their data is being used, and then creating a marketplace so that people can go and learn more about themselves or even earn for making their data available for research purposes. So I'll switch gears slightly here and jump on to a discussion of how Weavechain's mechanism works for this blockchain anchoring. And the first thing I like to start off is sort of like, what is the problem that we're actually solving with the security scenario? And I like to pattern it after, I like to use HTTPS as an example. That little lock icon in your browser that shows that you are actually on docs.google.com. This technology took 25 years to materialize, but what really we're doing with HTTPS is ensuring that I can securely communicate with another party. And it solves for the ability to have a fake version of my counterparty and for somebody to go and tamper with my communications between them. With Web3 technology, what we're trying to do with the consensus algorithms is make it so that we can all be writing to a shared database where it's impossible to have, an unpermissioned party D tampering with our database, and it's impossible for any party to actually go and tamper with that history. So for our mechanism, the way we go and guarantee this is saying, if A is going to initiate a write, we're going to go and establish a consensus leader to go and write to the blockchain. The network will go and write to their local database and then update the blockchain over here. The result of this is a tamper-proof shared database between A, B, and C that leverages both blockchains and databases.
I would jump in a bit to say that the consensus leader is there just to prevent denial of service, but the integrity of the data itself is guaranteed by signatures from the source. So
yeah, exactly right.
Yeah, that's a very important thing. And also, the consensus can happen. I mean, this first consensus is in order to establish who is writing to the blockchain. But the write to the blockchain itself is done with a threshold signature that is gathered from all the parties, and the smart contract that stores the hash is actually checking the threshold signature. So even what I try to convey is that even if there is a leader chosen, that leader cannot be malicious because it still needs, there are other mechanisms in place.
You got it. We can actually dive in a little bit deeper over here, right? When that write application is happening from A, they're going to go and send not only the data, but also a hash of the data and their signature to the Weavechain node. That is then going to go and establish consensus with the network by saying, okay, we'll figure out who's going to be that consensus leader using our PBFT algorithm, I believe. And then we'll validate that this application is valid. And then when the network is going to go and update their databases, they're also going to go and validate the data signatures and hashes before they write it locally. And then they can go and update the blockchain. And here's where they utilize that threshold signature that you just mentioned between A, B, and C to make sure that they're all valid. And once that threshold has been reached, then we're going to go and actually update the blockchain between all these parties. So this is pretty complex technical stuff. We've gone and put together some pretty simple definitions over here if anybody needs to dig in, and we encourage you all to reach out to us if you have any questions. Whew, that was a deep one, Johnny. Do you think there's anything else that we should chat about with regards to the blockchain anchoring or guarantees of immutability?
Probably to say that the blockchain anchoring is can be done in different ways. We have the time series anchoring, and we have Merkle roots anchoring.
Oh, that's right.
Those are two different ways of guaranteeing the time series immutability.
Oh, that's a really fun one. So maybe we could go and dig in a little bit deeper there. So let's say that we go and have a database of hospital records in this case, right? One row per hospital. If we had a series of hashes here, they could each represent a batch of the data. And for your time series methodology, you're saying that you would go and post, each hash in the same smart contract, right?
Yeah, there is a hash for each batch in the time
Data
series.
hash for each batch in the time series.
We do some batching, which is optional and can be done by size, by time, by sort of time. So
like here, it was 1,000 records, right?
Yeah, 1,000 approximately. Probably the 4001 49999 hit the threshold time. So here it was
Oh, funny.
It's mixed. So the default hashing is by count and by maximum wait time. So yeah, in this methodology, we batch our records together and we actually compute the hash of hashes. And that's the batch hash. What this means is that, so it's optional. Somebody that does not need a high throughput can use a batch of size 1, and then you have a signature for each record. There are advantages, meaning that there is less data stored on blockchain. When you do batching, there is high throughput. But the disadvantages are, I mean, they're not. It's pros and cons. You have to tune it. The disadvantage is that in order to check the hash of, to check the integrity of one record, you need to check the whole batch.
Right. So you're saying if I want to go and verify, that this record was okay, I would have to check the entire batch from 1 to 1,000.
Yeah. So you have speed at write time, but you are slower at validation time. It's always a trade-off.
Right. And then, how does this change if we were doing the Merkle tree method that you mentioned?
There will be a single hash that is stored in a smart contract for a collection.
Just that Merkle root, right?
Yeah, just the Merkle root. And in addition, so we'll have a different approach there. We also store, so we have the timestamp, the root hash, and the signature from the source, because the Merkle root itself needs to match also the Merkle tree that is available. So a user that needs to validate the data can obtain the Merkle tree if it's permissioned, or check somehow in the Merkle tree remotely via confidential compute the inclusion of a piece of data or the validity of some piece of data.
Just trying to see. I don't think I have any good diagrams of our Merkle trees.
It's a standard Merkle trees. Well, at least with, of course, configurable hashing.
Maybe
we actually also have Merkle trees, but they are not, let's say they are in lab mode. They are not production.
For sure. But I think the key idea here was that we would go and take a Merkle tree that has, all these different leaves inside of it. Let's say one for each record. And then they all roll up to this one Merkle root. And you're only going to be storing that Merkle root in the smart contract, right?
Yeah, correct.
So instead of every single batch, it would just be one Merkle root, and that would update over time.
Correct. And the node that wrote the Merkle root, it can be a provider of the full Merkle tree if it's needed. And you can match or validate the Merkle root in the Merkle tree.
And this is what most people are doing for their proof of reserves implementations, like Binance. So, if you wanted to go and validate that, Binance had your specific position in its balance, you would come to your dashboard, go and get your Merkle leaf over here, go and download the Merkle tree, and then verify it against, make sure that that Merkle tree came out to this same Merkle root hash, which they have announced publicly. And this hasn't been posted on a blockchain, but it has been displayed publicly in a way that I'm sure many people have scraped in order to make sure that they are not cheating over here. Well, a lot of fun with a different kind of anchor over here. Let me just see, blockchain anchoring. I'll just make sure right over here we have hashes and batches, and then Merkle roots on chain. We didn't get to talk about lineage today, so maybe we can dip on that a little bit next week. What else do you think we've fun to chat about, Johnny?
Yeah. So lineage is a complex topic. It will be data lineage and computer lineage. It's already a lot to talk about. Yeah.
Oh, nice. The computational lineage is a lot of fun. Oh, and our AI example. That's right. Yeah. Why don't we stick with that for next week?
Yeah.
And we can leave it at that for today. Well, pleasure chatting as always, Johnny. Thanks so much, and catch up more next week.
See you.